Hello everyone and welcome to a new discussion which we are going to have under this course which is groundwater engineering, and discussion which we are going to have about the aquifer boundaries. You know, there are not only we have been discussing confined and unconfined aquifers, that means most of the time we have been discussing about the boundaries vertical sense, that you are having a semi confined a clay layer, then sandstone, then clay, and that makes your confined aquifer. So, you are having impervious layer, pervious layer, impervious layer, or in unconfined aquifer conditions below a pervious layer you are having unconfined or impervious layer, and the top part is open for piezometric pressures or water table. But what about the boundaries in horizontal direction? So, whatever we have been discussing about the boundaries in vertical direction, now we will try to understand the effects of boundaries, aquifer boundaries in horizontal direction. Again, this figure is familiar to us, but this helps us to understand things in a much better manner. So, when we go for these solutions for groundwater problems, we assume that aquifers are infinite in existence, but which is not true. These things end even in alluvial plains, they may not continue for kilometers together. So, we have to think in that direction, that each aquifer is not finite, there will be boundaries, some interruptions, some, or in hard rock terrain, and there might be dikes or quartz reefs or faults or any other structure which will truncate your aquifer. So, we know that no finite aquifer exists anywhere on the world, and ultimately then all aquifers have boundaries in a horizontal direction too. And hydrologically there are two types of such boundaries which we consider in groundwater engineering. One is the recharge boundaries and another one is the impermeable boundaries. So, like here we are having a recharge area, like you can see in the center, and then you are having a pumping well. So, then in between there will be a boundary which is controlling the recharge, and therefore, the flow lines will be also accordingly which we will see. So, if we consider the recharge boundaries, like here in the left bottom figure which we are seeing, that there is a river, and this river is hydraulic connected with aquifer, because this is a unconfined aquifer condition, and this is the well where from where the pumping is being done, and this pumping water level or the cone of depression is also shown here. So, this recharge boundary exists when an aquifer is in hydraulic contact with a perennial stream, lake or sea. Now, up to lake it is fine, but once this hydraulic boundary come in contact with the sea, then there will be lot of problems. The problem is because sea will have altogether a different type of water, saline water, and other sediments and problems. So, that water is not fresh. So, if this intrusion occurs, then there will be really big problems for groundwater, for fresh groundwater. So, in the coastal regions this is a very serious problem. If lot of water is withdrawn and this hydraulic gradient increases significantly, then the sea water can enter into aquifers, and then our aquifers becomes useless from fresh water point of view. So, therefore, if there is a stream or lake, it is fine, but if it close by is the sea, then or any lake which does not have the fresh water, then all kinds of precautions should be taken for these aquifers, and whatever the water, fresh water is being withdrawn. There may be a impermeable boundary which is a complete terminates against the, so aquifer completely terminates against the impermeable material as shown here, that these rocks are impermeable. These are might be the, on the left side you are having sedimentary rocks, and then this boundary is completely impermeable, will not allow any water to flow, and therefore, if you see the drawdown or the cone of depression, the shape is not a perfect cone, but it is having a more hydraulic gradient than in this part, because here you are having supply of water, here because of impermeable boundary or material you do not have. So, these situations will also come, and this cone of depression can become deeper very quickly as compared to boundaries as we have seen in the previous discussion. So, if it is river or lake, then this cone of depression on both sides will remain same. If it is impermeable boundary like this, then shape of the cone of depression will change completely. Now, in these impermeable boundaries cases, these boundaries exist where impermeable materials such as sand and gravel grades into impermeable materials such as silt and clay. So, within even sedimentary formations, if we encounter clay layer or silt layer along with the sand or gravel layers, then this kind of situation, impermeable boundaries will occur. Or impermeable boundaries will also occur in valley fill which terminates against the bedrock, or which are on the sides and which are hard rock. So, these valley fill alluviums are good for getting fresh water or groundwater, but the sides of these valleys might be having hard rocks, and they serves as impermeable boundaries. And in hard rock terrain, this is a very common problem, that the river or this drainage system have developed some valleys which are later on filled with alluvium, and they become a very good aquifer. But in aerial extent, or I would say in horizontal directions, they are very limited by bedrocks, side bedrocks, and then your aquifers becomes though linear but narrow. Or these impermeable boundaries may be because they terminates along a geological fault, which I also discussed. Maybe a dike, and which is made from some rocks like igneous rocks, which may be completely impervious, or maybe a quartz reef. So, if I give the example of Bundelkhand granite or this granitoid in the central or north central area, a large part of the country is under that, and you would find that there are hundreds of quartz reefs which are running roughly northeast to southwest direction, and some of the quartz reefs are running for hundreds of kilometers. So, these boundaries, quartz reefs serves as a impermeable boundaries, and they do not allow generally water to flow from one direction to another or across these. So, they may also serve as impermeable boundaries, but some advantages can also be taken. This is a kind of blessing in disguise. So, when the groundwater exploration or recharge, an impact of recharge, we will be discussing these quartz reefs in a granitic terrain, and how these disguise can be served as blessing. That part we will also discuss. Anyway, so these aquifer boundaries, what is our purpose is to see the hydraulic effect of such boundaries, and then how, in what way it is affecting our aquifer yield, how much water we can withdraw, and how the cone of depression, the shape of cone of depression will take place. So, all these equations, especially Darcy law and Thyme and others, they are devised to determine the transmission and storage characteristics of aquifer. With the exception of Darcy law, which are based on assumption that the aquifer being tested is of infinite extent, and we have just discussed that aquifers are not infinite, they are finite. So, we have to think in that direction, that how these things can be thought, and better estimations about groundwater and groundwater exploitation can take place. So, if the aquifer is being tested near one of its boundaries, like impervious boundaries or a boundary which is along the perennial river or this, then this fact must be considered during all kinds of analysis. So, a problem then is to develop a hydraulic model which will convert an aquifer of limited extent into one of the infinite extent, and this only through modeling it can be done. And this then we do through creation of or introduction of an imaginary well, where it is not there, but we will imagine and accordingly then our understanding will be developed. So, imaginary well in an aquifer of finite extent can be transformed into a finite or infinite aquifer. So, a finite extent of aquifer can be converted or transformed to infinite by introducing a imaginary well, and this is also called image well theory. So, this works for estimations of all these things quite well, and it has been practiced also. So, first we will consider the use of image well theory with respect to an impermeable boundary. So, here in the center, as you can see that impermeable boundaries is shown. So, hydraulic similarity between a groundwater divide and an impermeable boundary is this one, which is shown here. And then what the significant feature in this example is the boundary is that is no water crosses it. So, we assume that this impermeable boundary will not allow any water to go inside or come from that side also. So, in other words, what it resembles a groundwater divide, and this is a very common thing in natural conditions that we may encounter this kind of situation. So, here we are imagining that there are two wells, the boundary is there. So, in the this B figure we are having now a, in place of that we are having now a boundary. So, this image well theory is working, and now we are having a image well which is shown in dotted lines that tells that how the behavior of aquifer will happen, though it is impervious. So, the hydraulic divide can be formed along a impermeable boundary by assuming that an image well is pumping at the same rate and the same schedule at the real one, and therefore, these two cone of depressions would be, one is imaginary, one is the real one is there. Now, advantage what we would see that in such situations the analysis will involve the principles of superposition, by which drawdown of two or more wells is a sum of drawdown of each individual well, and that further step which we take in the image well theory. And the again further advantage when it is desired to obtain the head of any point under the influence of pumping at a constant rate Q through the real well, and then determine what fraction of pumpage is derived from the stream, if that kind of situation is there. So, in image this image theory or image well theory or image well model, the aquifer is infinite in extent. So, in the B figure, as you have seen that the no flow across impermeable boundary, but we are assuming that it is allowing the flow. So, that imaginary we are having after assuming that this is also pervious and it will allow the flow of water. So, we are considering now infinite in extent, particularly I am talking about in horizontal extent, and imaginary discharge well, which is a image well, exists beyond the boundary at this one, and the same distance from its real well. So, the boundary is here. So, this distance between real well is the same as the image well. This is what is considered. So, it is a kind of a mirror image, assuming a mirror image of a real well. So, in this groundwater divide develops between the real well and the image well at the position of the boundary, which you are also seeing here. This becomes our groundwater boundary. So, these values are already written here, both are same, x written, x value is written. So, recharge boundary is one along which there is no drawdown. So, recharge might occur here. Such boundaries exist if a aquifer is freely connected hydraulically with a body of surface water. So, this is what we are imaging here. Now, a recharge well is located across the boundary from the real well. So, now here what we are assuming that a perennial river is here, and then we take this thing and make a here in the no drawdown beyond a recharging boundary. whereas in figure B the drawdown of the real well is cancelled at the recharge boundary by build up of a image well. And now we are having a inverted cone of depression kind of imagination, that image well is here and this cone of build up rather than cone of depression, now we are assuming a cone of build up, and this is our recharge boundary which is there, the distance is same as x. So, then we are assuming that this is inverted cone or of depression, and that is cone of build up. So, water is assumed to be recharged through the image well at the same rate and on the same schedule as it is discharged from the real discharging well. So, a kind of balancing in terms of water withdrawal and water recharge is assumed here, and this will give many points of groundwater discharge under the natural conditions, which will represents the point of potential recharge under pumping conditions. So, this therefore, at many places where groundwater flows through floodplain deposits into stream under the non-pumping conditions, the direction of flow at the stream is reversed locally by pumping from wells, and the aquifer is recharged by the stream. So, this is what the scenario we are assuming in these two figures, that image well theory now applied here to the recharge boundary, and you can see that the recharge through the stream is assumed here. So, now what are the limitations of this image well concept or image well theory? The first limitation, that in nature few impermeable boundaries are absolutely impermeable. What it is means that all which the boundaries which we are saying impermeable may not be 100% permeable, and few recharge sources are connected completed freely with the adjacent aquifer. So, these boundaries might exist like this. Now, a movement of a small amount of water, because even in hard rock terrain, if it is weathered, fissured, fractured, some amount of water will move across. So, through these impermeable boundaries, and which will make the boundaries appear from image well analysis to further away as we are assuming actually it. So, if flow is occur, then these boundaries will come more close to the real well. This is what we get through, because even an impermeable boundary will may allow some flow of water. So, if we are having some recharge boundaries instead of impermeable boundaries, then few streams, lakes cut through the entire thickness of aquifer, they will of course bring a little different scenario as we have seen in previous just few minutes back. Moreover, the bottom of these streams, lakes are covered by a layer of silt or clay. Now, maybe silt or clay or maybe even gravels or coarse grain materials, but if they are there, then they will retard the movement of water into the aquifer. So, aquifer will get benefit because of these streams or perennial streams and lakes are there. And finally, as a result, the effective position of the boundary appears on analysis to be beyond the near bank of the stream or lake, and it will be more close to your rear well. So, we may overestimate that the distance which we mentioned in the slides as x may be x minus few meters because of this not perfect impermeable boundary, or maybe some recharge boundary or recharge sources like stream, lakes or some other things. But the point here is to remember, which I have just touched earlier also, that if aquifer is close to the sea, then all kinds of precautions in the analysis, withdrawal and recharge should be taken place. Otherwise, if because the boundary problems, the aquifer boundary problems in the coastal areas are a big problem world over, so in India also, and therefore the fresh water withdrawal should be done very judiciously. So, no way the sea water or the lakes do not have the fresh water, that water enters into our aquifer. So, with this I end this discussion, Thank you very much.